How are we doing with the homework? One? How many people done homework one? Hands up. Hands up. Almost. When is it due? Tonight. It's tough? I think the only tough problem is the one that's recurrences, which are not master theorem. That's the tough one. Yeah. So I want to talk just a little bit more about recurrences before I start talking about other things. We need to move on. But I do want to talk three things about recurrences. Hopefully we won't take that long with it. Let's see. Here's one example I want to do completely. It's an example that's not master theorem. So it's a kind of one that I think it's similar to one in the homework. I hope it's not exactly one from the homework. P of n is n squared divided by log n plus 4 p of n by 2. Is that the homework? No. I don't think it is. Right? All right, so this is even if you use the master theorem from the book, the one with f of n, it has that regularity condition with the epsilon. It says you have to be a little bit either plus epsilon or minus epsilon. And there is an example like this in the homework. I think it's n by log n or something. Then no matter how hard you try to fit that epsilon, never going to work. You can try, but you're not going to be able to apply the master theorem from the book or this one. Right. So you have to do, I guess, something very similar to what I'm doing here. Although it will be different because it's not the same recurrence. So we're going to do the brute force iteration. We're going to say, okay, what is this? I'm going to expand it. So I have the n squared log n. It may be a good idea to write this term first. I think last week we wrote it last. If you write it first, it builds up a sum in the beginning. So some people do that. I'm applying now the recurrence in here. So that's a 4. What is the recurrence in t of n by 2? It's n by 2 square, right? Divide by log of n by 2 plus 4t of n by 4. Okay, let's expand this thing. Let's see what we're getting. So n squared divided by log n. That's the first term. Now this term, I'm going to try to get rid of the 2 squared. That's a 4. Goes away with a 4. So I'm left with n squared by log of n by 2 plus 4 squared t of n by 4. Maybe I should write this 4 as a 2 square. Maybe that's easier. Okay. So now let's expand it again. We have an n squared divided by log n plus an n squared divided by log of n by 2 plus 4 squared. What happens now with t of n by 4? If I do the recurrence on this term, what do I get? N squared divided by log of n by 2 squared. So I'm calling the recurrence in for this term here. Plus 8 by 8, 2 cubed. N squared. I'm doing something wrong here? Square, like that. Not really good cube. Oh, it would be square. Is that good now? Yep. Yeah. Okay. Plus 4 p of the what power? What power? 3, right? Because every time I do this, it divides by 2, right? So I had divide by 2 2's, and I divide by another 2, I get 3 2's. Okay, so this is now n squared divided by log n, plus n squared divided by log of n by 2, plus n squared divided by, because now I get 4 square goes away with the 4 square in the front. So this is log of n divided by 2 square, right? Plus 4 to what power? Cube e of n divided by. Now, do you think we did it enough to find the pattern, or guess the pattern? Because that's the next step, guessing the pattern here. So if we do this k times, what would be the pattern? Looks like it's n squared divided by log n, plus n squared divided by log of n by 2, plus n squared divided by log of n by 2 squared, plus n squared all the way to log at n divided by k minus 1 maybe? I mean, depends how you want to go with this k. I'd say k is this value here, the 3, so that would be k minus 1. Plus 4 to the k, t of n divided by 2 to the k. That's the general pattern. After k steps. So we can write this concise. This is n squared in the front, right? Sum from I equal to 0 to k minus 1 of 1 over log of. We can even decompose those logs, right? That'll be n divided by 2 to the I, right? So that's the first sum, plus this term, 4 to the k of n. Now, formally, if we want to be really formal, which is not really necessary for this class, except I'm asking you specifically to do that, there is a proof by induction here. We say, we guess that pattern, and now we're going to prove pattern by induction. So we want to prove that this is the general form after k steps. So there is a base case that you have to deal with, but that's very easy. And then what's the inductive step? If this is true for k, so inductive step is if after k steps we have that t of n equal n squared sum from I equals 0 to k minus 1, 1 over log of n to the I plus 4k t of n to the k, then what? So if we have that relation after k iterations, then after k plus 1 iterations, we must have t of n is the sum of I equals 0 to k of 1 over log of n divided by 2 to the I plus 4 to k plus 1 t of
n by 2 power k plus 1.
So if you want to be very formal, when you guess the pattern, you have to prove that that's actually true. So that's an easy proof. It only takes this to run the iteration one more time. If I start with this formula and I expand this one more time, I'm going to get that formula, right? It adds the next logarithm term to the sum, and this will be 4k plus 1. So it's not a big deal. We usually don't require this kind of proofs if you guess the formula correct. And if you have if it's clear where how you got it, like here you can see the logarithm sum comes from this expression here, and this is that one here. Okay, so how do we finish this then? We got the pattern. Now we have to calculate it, right? So we have this last k. What's the last k? When does this thing stops? This inside the t has to be about 1. So we need k about log base 2 of n. So if case is, if that's the case, what the sum gonna look like for that k? So for k equal log base 2 of n, what we're gonna have, t of n is the sum from I equals 0 to log n minus 1 of n squared is in the front here. 1 over log. I'm going to expand that log. It's a log of a fraction. So how much is a log of orange divided by the apple?
Log of orange minus
Orange minus log of the apple, right? So that's log of n minus log of 2 to the I. It's minus because it's the orange by the apple, right? Plus 4 to log n, that's log base 2 of n. And of course inside we're going to have t of 1 because that's how we pick that k, to get t of 1 inside the t. Who's with me? Hands up. That stuff is going to be easy, right?
N
How much
squared.
is 4 at log base 2 of n?
N squared.
That's n squared, right? So this is n squared t of 1. We're kind of done with this term. T of 1 is a constant. We don't know which constant, but it's some constant. So this is obviously theta of n squared. That's the first term. Done with it. Now n squared is n squared in the front. I need to look at this sum and say, what is this? This requires a little bit of creativity here. Log of n minus 1, right? This is 1 over log n minus I. So now I would like to think of this sum not in concise form, but in actual expanded. What are the terms that are being summed here? Let's start with 0. If I open this sum up, what do I actually have? What's the first term? 1 over log n. What's the next term? Log n minus? What's the next term? Log n minus 2. And what's the last term? When I is exactly log n minus 1. 1 over 1. So I think I want to write this sum in a concise form, but thinking from the other end at it. So this is going to be theta of n squared plus n squared. Sum. I'm going to change the index. When I usually do this, that's for myself. You don't have to change the index, but just to be clear in my mind, what is it that I'm doing? I'm going to replace this I to not get confused. If I put I here, I'm going to get confused. But I'm going to replace it with j, and I'm going to say, okay, where do we start? Maybe with 1. Let's start with 1. It's going to be 1 over j. Because I start from here. 1 over 1, 1 over 2, 1 over 3. I'm assuming this log of n is a natural number. It's an approximation. Right? So what's the last j that I could go to? Log n, right? You can say that's approximative. It's the same order of growth for sure. It will be exact if this log n will be an integer. Now, assuming n goes very big, we're not concerned with n equal 3 or 4 or 5. Suppose n is 10,000. Log of n, it's not an integer, but it's, for all practical purposes for the growth here, log of 10,000 is about what? Log of 1,000 base 2 is about 10. You got 13. It's 13.3 or something. I can approximate it with 13 as far as the order of growth goes, because in general, when n is big, it won't matter the 0.3 part, right? If you want to be really exact, you have to put ceilings and floor to these things, but as I said earlier, you can approximate it just as well like this. For monotonic increasing function like logarithms, it's the same thing. Okay? Another way to do this is to change the variable from n into 2 to the n, and then you got the approximation for free. Everything is going to be an integer when you do the logarithm. Anyway, so now I'm here. Again, what happened here, I changed the index from I to j, and I counted this sum from the other end. So what is this now? That's theta of n squared plus n squared. What's up with this sum? It's a harmonic sum, right? 1 over 1 plus 1 over 2 plus 1 over 3. The harmonic sum up to some term t, that's 1 over 1 plus 1 over 2 plus 1 over t up to t. It's approximately what? Log of t plus a constant. So this is going to be log, again approximately, the t in here is the log n. Right? So log of n, to be exactly correct, this is like that, like log of n. This is theta of n squared plus theta of n squared. We write that log n. Log n means log of n. So we now between those two, which one's bigger? It is true that log n goes to infinity because n goes to infinity, log of n goes to infinity, so log n goes to infinity. How about log of n?
Infinity.
Goes to infinity, right?
Yes.
But if I take one more log, also goes to infinity.
Yes.
However, you should know, this is called the Ackermann's properties, that if you take about 4 logs or so, like I did here, for all practical purposes, this is effectively a constant. Now, theoretically, it goes to infinity, because n goes to infinity, therefore log of n goes to infinity, therefore log of something that goes to infinity, so on and so forth. In theory, you can take 6 more logs, and that goes to infinity. But if you think about what this means, for this to be, let's say, I want this to be about 2. What n needs to be? So this is 2. How this n needs to grow to have this kind of, that will be 2 at the power 2 at the power 2 at the power 2, and so on and so forth. The moment you have this situation, say 5 of them, 2 at 2 at 2 at 2 at 2, this is a very big number, right? So in practice, it is true that taking a bunch of logarithms to each other, you go still an infinity function, in theory. But in practice, the moment you take 4 or 5 logarithms, for all practical purpose, that's a constant. For any computer, count all the atoms in the universe, whatever. After 5 logs, you got a constant. So this is the Ackermann functions, the guy who studied those kind of things. And they say after 5 logs, it's pretty much set. Anyway, that's the answer here. And I think this is similar to one of the recurrences that you have there. The other 2 things that I want to say really quick before I move on about recurrences. Somebody asked me yesterday about one that's, I think, T of n is T of n minus 2 plus n squared. Right? Not a complicated problem, but I thought I'll walk you through the beginning of it. I won't give you the answer. It's the same like in here. What happens here, it's easy to see with the iteration brute force method before you start applying anything. Is every time I take 2 units out of it, start with the n like 100. If I take 2 units out, I have to dump an n squared. I take 2 more units out, I dump n minus 2 squared, and so on and so forth. So if you have to expand this, let's write it differently. N squared plus 2 n minus 2. Right? That n squared applied again here, I get what? N minus 2 squared plus n minus 4, right? So I got 2 more units out, but I dumped n minus 2 squared. Again, n squared plus n minus 2 squared plus 4 squared plus.
Say minus 6.
Now, of course, this is going to go eventually, after k steps, to t of 0. After how many steps that goes to 0?
N by 2.
I take 2, 2, 2, 2, 2. How many 2's I need to take out before that becomes 0?
N by 3.
After k steps being n by 2, that will be about 0. And what's going to happen in here? After k that many steps, I'm going to have n squared plus n minus 2 squared plus, what's the last square that I'm going to take out?
2 square.
And it's going to be like a 2 square.
Square plus, yes.
So that's the sum of even numbers squared, more or less, which you can easily do with the formula. I mean, if you take a 2 out, or 2 square out, becomes 1 square plus 2 square plus 3 square. That's a formula for that. But even without it, you can do it by induction or come up with a formula for it. Okay? So I want to mention that. Easy to do that way. And I want to mention a third thing as an extra credit exercise for talented mathematicians among you. It's a little bit of an expansion of master theorem, but I don't want to do it as a proof, as a theorem in class. I wanna ask you again as a fancy math, try to prove it. So suppose I have a recurrences that says T of n is not like in master theorem. Master theorem, it says a plus n by b plus n to the c, right? That's the master theorem. I wanna, what this does in fact, it says T of n by b plus T of n by b plus T of n by b plus nc. How many times is this count? 8 times. So suppose I do the same. This 1 over b is a kind of a ratio here, percentage of n, if you like. Suppose I don't do this. That's master theorem. Suppose instead I have something like T of n. I give you a simple case, it's more general. But suppose I have some sort of coefficients, b1 or 1 over b1. If you want to think in the same form, it's 1 over b1 times n plus another that's 1 over b2 times n. It's not the same b, right? Plus T of 1 over b, say m. Some b, bt or something, bn. Plus the simple version just n. I will skip this c here. Let's just not worry about that one. So for an example, I could have T of n is 1/2 of n, right? Plus T of 1/3 of n, plus T of another 1/3 of n, right? Plus T of 1/4 of n. See, my b's in here are not like in master theorem, the same b everywhere. It's 1/2, 1/3, 1/3. In fact, they don't have to be 1 over an integer. These b's could be any coefficient. 1 over b could be 2.75, or 1 over 2.75, 1 over 3.33, so on and so forth. So then I have here plus n. Let me write it there. So I'm adding this n. What I'm saying here works for n to the c, but I don't want to worry about that n to the c for the exercise I'm going to give you. So that's an example where I still have fractions of n. So I'm not talking about n minus 2. That won't fit in my example there. I still have a fraction or some coefficient times n. So what I want you to prove for this form here is that if the fractions, all of them, sum up to less than 1. So like for example, 1/2 plus 1/3 plus 1/3 plus 1/4, how much is that? That's more than 1, right? So that won't work in here. But what if I have 1/2 plus 1/4 plus 1/10? That would work, right? That's less than 1. If the fractions are less than 1, then P of n is n. Oh, technically over is linear. And that works for n to the c. But what I want you to prove is that, obviously that will work in master theorem. If in master theorem, how would I write this for master theorem? All b's are equal. So the master theorem version is all b's are equal, b1 is b2 equal b3 equal bm. So the condition, this condition master theorem means what? What means the sum of b's more than 1? How much is the sum of b's in master theorem? A by b. So if a by b is smaller than 1, then b of n is eta over. Which is easy to see if you remember master theorem. Because if a by b is smaller than 1, log base b of a will be smaller than c, which is 1. So it's that case that says that, to be linear. But I want you to try to prove this mathematically, so I'm in a complete proof. Not for all b's equal the same, like in master theorem, but for some, any coefficients b's that just sum to less than 1. I think you have a exercise. Which one is that exercise? P of n equal, what is it? N by 2 plus n by 4 plus n by 8 plus n or theta of n. How much is, what are the b's here? 2, 4, and 8. How much is 1/2 plus 1/4 plus 1/8? 7/8. That's more than 1. So that the whole thing is going to be linear. Right? So that's actually a big hint, because if you start this for that, anybody tried this for that exercise? It gets monsterly pretty fast, right? It's useful to know this. Now you still have to prove it. I mean, if you prove this, you can just apply it to that exercise and be done with it, right? Because clearly it fits in there. But if you don't prove this, you don't get any points for this. When I say extra, it won't affect your grade. Extra means if you want to learn more. So I'm happy to help you with that at office hours, but it won't be for the grade. It's just for your own development. Okay? If you don't prove this, you still have to do this problem somehow, prove it by induction or something like that. That's a good thing to know. If the fractions add up to less than 1, it ends up being linear. We're going to need this later on next week or the week after when we talk about quicksort. So that's all I have to say about recurrences. And with this, we want to move on to the next chapter. I erase some things here. So there will be a new homework very soon posted. I already said on Piazza that people who register late can have few extra days for homework 1. You just have to show the TA the registration email or anything that says I registered late. Late means after the first day of class. If it's not on January 8th, you got an email after that you registered, you can take a few days. That extension will not roll into homework 2. You're not going to get a homework 2 extension because you're late on homework 1. Okay? So I'm going to post homework 2 today or tomorrow, even though you may still working on homework 1, and you can start from there. I should warn you that homeworks 1, 2, 3 are a lot easier than homeworks 5 and 6. Just a fair warning. If you think this was a hard homework or the next one that take 10 hours, I would expect the dynamic programming homework to take 3 times that time. Fair warning to plan your life accordingly. Homeworks will not change. And we had this issue every year. I teach this class. It's my 10th time teaching this class. And the people say, are you crazy? Like, I have to drop everything to do this homework? Yes, maybe. You cannot avoid dynamic programming. I'm assuming this playing with mathematics, more or less, everybody gets. the core part of the course is not playing with mathematics. It's understanding dynamic problems. So we'll have to do those homeworks. Okay. Now, we're moving on to sorting. So chapter 2, we're done with the introduction. Chapter 2, sorting. So before we do sorting, I want to make sure we all understand what the binary search tree is. So the chapter is about sorting, but before we do so, I want to make sure everyone understands what a binary search tree is. So recap. Binary search tree. I'm assuming you've seen this before and you know what it is. So what is it? Okay, I have a tree that's binary means what in a tree? Everybody has 2 or 1 or 0 branches. Right? So here's my tree here. Now not all branches are equal. Maybe this one stops this way, and then this one expands more. And then this one here expands more, and this one expands even further. Right? That's possible. And now, so I'm going to put some values. When I put values in the tree, I typically do like in an array. The value goes inside the node. And if I want to label these nodes A, B, C, D, I'll write the label outside the node. So let's just say I have a 15 here. I'm making this stuff up right now. This is a 20. This is a 100. This would here would be something like 80. This would be something like 70. This in here would be 90. If I have something here, that would be 110. This 20. So this is a 10. This would be a 40. This here would be a 45. This in here would be what? 30. How about this? 35. 25. So this tree obviously has a magic property. I like the word magic. You don't have to use that word, but you should create a word for this kind of thing. There is a key property of a tree, and we're going to see today of a heap or a search method or something. There is a key mechanism that allows it to work. So you should always, when somebody shows you something in an interview, in a problem, in a homework, in an exam, you have something to solve, you study a new method. After you maybe get a little bit familiar with the problem, the most important step in understanding what you're doing is understanding that key property or key magic property that allows it to work. Why is this tree better than some random tree or a heap? How does a heap allow us to work? Or what is it in quicksort that makes it work so well? You know, it's true you have to know the story, the whole thing, but there's a key property that you need to have to make things work. So what's the key property? Magic property. Every value in a node, so I say value, node value, is smaller than and bigger than something. Left, and this is right? So many people put left child and right child. That is not the magic property. That is correct, but not good enough. Left sub 3. So it's not just saying this 50 is bigger than 20 and smaller than 100. I know you guys knew that, but that's not good enough to make a binary search tree. This 50 has to be bigger than the entire left sub 3. That is this whole thing in here. This is the left sub 3. Then this is the right sub 3, right? And that happens for every node value. So it's not just the root. pick this 100 here. This 100 is bigger than its left subtree and smaller than its entire right subtree. So anything that's coming out of this 110, even if I go left, 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 left a bunch of times, left is smaller than a 10, right? Left is smaller than this, left is smaller than this, left is smaller than this. What's up with this value here? Has to be bigger than 100. So once I move right, even though I move left many, many times, all these values have to be bigger than 100. That's one thing that you should take a look. I think those things are somewhere in the book, maybe chapter 12, is the notion of successor and predecessor. We'll talk about those a little further down the term, but if somebody says, here's a node, this 80, and you have the full binary search tree, right? As a binary search tree, it's valid. Valid means it must have this property. What is the next immediate higher value to this 80? Where can I find that? I'm assuming I can navigate this tree in all directions. I put my hands on a node. Where is the biggest immediate value? Where can it be? But that's not guaranteed. There's another place where bigger values might be. So how about if I move, the parent has to be going in what direction to be bigger? So everybody has a parent, but I have to move slightly to the right or to the left to have a bigger value. If this has to be a left child to get a bigger value to the parent. And once I get a bigger value to the parent, so like in this case, 100, now if this thing, 100, is the left child of, the right child of somebody, like in this case, right? 100 is a right child. What about this 50 compared to the 80? 50 is more, so that's no good, because I'm looking for bigger values. But what if 100 is the left child of somebody? What's up with this value here? Okay. So where are the bigger values? Either on the right side, but once I move right, after 90, where should I go to find the next immediate value? Left, right? Or going up, right? So how about you guys try to write a function, successor or predecessor? Predecessor is the one immediately smaller. Successor is the one immediately higher. It says, giving a tree, write a function that for any node, if somebody gives you a node, like a pointer to the node or something, find the next immediate higher value or smaller value. I think this might be in one of the homeworks, but it's a good exercise. How do you think of a binary search tree? It's all assumed to be undergraduate material, so I'm not going to insist on it. Just a quick recap of what binary search trees are. So now, the next thing we need to do is to recap some sorting methods. So successor of a node and predecessor of a node. Okay, recap, sorting. Here's one that everybody loves, bubble sort. I'm sure everybody have seen this, right? I'm going to assume I have an array here. It's an array with values, size n, right? 1, 2, up to n. And I need to sort this array. Sorting might work on other data structures, but typically we look at arrays. How does bubble sort works? I swap values, so the internal of bubble sort is going to be if some condition, right? The idea is to swap a of I with a of I plus 1. So the core idea in bubble sort, if two things that are next to each other are not in the right order, swap them. So what's the condition? What does it mean not in the right order? A of A is bigger than A of A plus 1, right? That means, because typically I want an array when I say
Ascending
sorted,
order.
I mean increasing order, unless I say decreasing, but if I don't say anything, sort means increasing order. So the core condition inside bubble sort is every time you see two things in the wrong order, swap them. Right, so now I have to add the rest of the pseudocode. Okay, that's the mechanism that makes the changes, but then how do I run it? So how do I do this? I'm going to say something like for I equal 1 to n minus 1. I'm putting some question marks here because I want you guys to fill the blanks. I'm not sure that's correct. You have to think about, you really want to swap this, and then once I swap this, I may swap it further and further and further, or I want to jump over the swap. In other words, suppose I swap these two values here. Do I want to continue when I moves to the next one? Do I want to move this value further if necessary?
Yeah.
Or I want to skip those two, jump directly here? I don't know. You have to think about that. This for loop is a controlling for loop. It is true that as a mechanism, everybody understands this. If this is a bubble, right? This whole thing is called a bubble, when two things consecutive are out of order. Or mathematically, it's called what? It's called inversion. When people talk about permutations, when two things in a permutation, I permute the numbers 1 to 10. If two things are out of order, that permutation has an inversion. So in mathematics, it's called inversion. In computer science, for some reason, we call it a bubble. I honestly don't know why, but we could call it inversion from the beginning. Right? So then, suppose you guys fix this for loop here. So this is exactly how it works. Now what? That's one pass through the array, perhaps fixing some bubbles, right? And then?
One more pass. The highest will be to the right.
What's the second for loop we're gonna do?
Will come from right to left.
From the I to n.
So this does what? Traverses the array once and fixes a bunch of bubbles, right? It may fix one here. Maybe if it goes next swap, maybe it takes the same value that just got swapped, swap it again, and maybe now it stops and then goes here, do some other swaps and finishes. Am I done? No. In one pass, I can't fix the whole array. So I don't think I need a for loop. Maybe I can do it a for loop, but in my mind, I can just ask, am I done or not? Should I go again from the beginning of the array and try to fix more bubbles? So how do I know to go again in the beginning?
Flag variable.
A flag that says, right? So I want to say, repeat this loop here. This is a loop, right? Until flag is 0. So what I want to make this work in a computer science way, it's a loop, right? I declare the flag equal 1 or 0, whatever I want. I say, as long as this flag remains 1 or something, you can declare it any way you want, right? Maybe the standard way is to start with 0 and say, if the flag remains 0, stop, right? Don't continue. But this loop will have to change the flag somewhere. When do I say keep going with the loop?
Once you swap.
Once I make one swap, I'm going to tell it keep going, right? So if there is a swap in there, I'm going to make the flag equal 1. So when is this going to stop? When is going to say stop? I started with 0. Every loop starts with the flag equals 0.
Yes.
If the flag is 0 here at the end, means what?
There were no swaps.
Means what? There were no swaps, right? So flag equals 0 is equivalent logically with no swaps. Now, is no swap the mathematical guarantee that the array is sorted?
Yes.
If I went through the array
Yes.
and I didn't find anything to swap, meaning all the pairs were in the right order. 1 was less than 2, 2 less than 3, 3 less than 4, 4 less than 5, right? So that's equivalent mathematically with what? A of 1 was smaller than A of 2, smaller than A of n, right? So because there were no swaps, the array was sorted, therefore I could stop, right? So I can say here, stop. Now you're gonna need a little bit of argument or proofs like this in your pseudocode. In this class, it's not enough to put a correct pseudocode and say, I'm done. You're gonna have to argue, although informally, I'm not expecting mathematical proofs. Why is this a good thing? Why can you stop if the flag is 0, meaning, since you're stopping, the array must be sorted? It will be a big penalty for all exams and homeworks if your thing is incorrect, meaning you stop, but the array is not sorted. It would be a far less penalty if your argument is correct, but your argument is a little shaky. Like, I think it works, but I can't really explain it. That's much more tolerable than having a piece of pseudocode that's just broken, like doesn't work. I mean, it depends how broken it is. Now, everybody can see the intuition that when, in here, this is a very simple argument. If the flag is 0, there were no swaps. If there are no swaps, they gotta be in order, so I can stop. This will be enough of a proof for this argument. So I'm not expecting very formal mathematical proofs, but I'm expecting an argument why the algorithm works. Okay? So that's bubble sort. How long is this gonna take? Y n squared. This loop here takes inside loop phi of n. And in the worst case, we didn't talk yet about worst cases, but that's what we're gonna be most preoccupied with, worst case. How many times I have to loop this?
N minus 1 times.
So worst case, also theta of n. Now n times n, that's n squared, right? Overall. But this requires an explanation. Why is the worst case n? I think this does not require an explanation. People can see that when you traverse the array, even if you don't do swaps, just traversing the array for I equal 1 to n minus 1, that's going to be a linear time algorithm, right? Whether you do swaps or not. So I don't think that needs a big explanation at all. I'm traversing the array once, is linear. But why is the worst case in here? There's no for I equal 1 to n here. That's what you're saying. But see, in my case, I don't have a for loop. Why is the worst case linear? Maybe I'm always done after log n steps or square root of n steps. In here, to show this, you need to make an argument about that worst case. Now, that can be informal. But why is the worst case? Why I need to repeat this if I have the worst possible input? Right, but I agree. In descending order, we'll take n loops to do this. But why?
Because every time it has to go into the for. Every iteration is a swap.
Yeah, but why is it going to take? So we're not talking about this for loop. This for loop is traversing the array once. We're talking about the main loop. Why is the main loop required to run about n times?
Flag level is updated for
Every
So heads up, so one at a time. Yes.
Every time the highest element bubbles to its place, its correct place. Right? At every iteration, the element goes to its correct place. So we'll need at most n iterations.
At most, yes. But that's not the argument I'm looking for. Of course, at most is going to be n times. I mean, that's easy to show that you're never going to need more than n things here. But what I'm saying, there are some cases where you need n things. When you say at most, maybe it's log of n, right? What I'm asking is, so that's actually a good point. Why is never more than n? There's two proofs here. One is saying that this will never, the outside loop will never be more than n. And his argument is you don't need more than n, no matter how bad it is. By the way, if you prove that one, it's not enough to say, look at the case that's sorted in opposite order. That's just one case. But this is saying in all cases, the outer loop is at most n steps. So that's his concern. My concern was not that. My concern is, are there any cases where it's actually n steps? You can do it faster than over.
When the smallest number is at the end,
It's gonna take n steps to get it back.
get it back to the first. When the smallest number is at the end of the array,
Yeah,
you need n steps to get it to the first place.
and
Steps to get it to the first place.
so I think there's quite a few arguments. I think you're correct, but you know, explaining that it's not as easy. What you just said doesn't make a complete explanation. You know, I think there's a bunch of ways to explain this, and my point here is that while bubble sort intuitively it's very easy, you're gonna have to put up an explanation. Now it's not rigorous, not mathematical, but has to be complete. The easiest explanation here for why in that case, or in some case, we need at least n steps in outer loop is this. How many bubbles can one pass in the array fix maximum? N. These can fix at most n bubbles. There are some cases, the worst cases, that have how many bubbles in them in the worst case? N choose 2 bubbles. You guys know this n choose 2? It's in how many ways I can choose 2 out of n, because everything is a bubble. So this actual number is n times n minus 1 by 2. So if I have that many bubbles, and one pass can fix at most n of them, how many passes I need at least? N minus 1 by 2, right? So that will give me a linear number of outer loops. It says, that's a mathematical argument, right? Maybe it's called pigeonhole principle, right? If you need to deal with so many problems, right? And every pass only deals with n of them at most, then how many passes you need? You need at least that many passes, right? But the other question is also good to answer, which is, it will never need more than n passes. And no matter how the array is, after n passes, I'm done. You can think about that. Why is it that if I do this, I'll never need in the outer loop more than n steps? Something to think at home. I want to move on now, because this is supposed to be recap from the college. We're going to need, when you put up algorithms, you're going to need these explanations. All right. How about insertion sort? Everybody knows how this works, insertion sort?
Yes.
So I have an input, right? Say the input is let's say, as an example, 5, 20, 1, 8, 49, 9. What the insertion sort does, it first of all reads input in order, keeps partially sorted array so far, and then inserts the current value in the correct spot. That is to maintain partially sorted order. So you can think of insertion sort. If I look at, say, so far I've done with those values. I want to think of insertion sort starting in the middle, not from the beginning. In the middle of the algorithm. Suppose I'm already done with those values. So this is in the middle. If I'm done with 5, 20, 1, 8 input so far, so that's done, and this part is still to come, I haven't read yet these values, 49 and 9. What must be the case in my internal data structure? This must be already sorted, right? So what would be the order?
1, 5, 8,
5, 8, 20. So that's my current, that's data structure. It's an array, of course. So I have this sorted partially. I'm landing right in the middle of insertion sort to figure out inside how stuff works. Now I'm reading this value 49. Actually, I don't want to do this. I want to do up to 8. So I'm done here. 521. So I have 1, 5, 20. And now I'm reading the next value 8. This is the current value. I need to insert it into what I already have.
Yes.
If people play cards, when they take the cards usually from the board, like in bridge, they like to sort it in their hands. So you see a lot of players that they put a card, they put a second card, third card, they keep it sorted in their hand. They take the next card, they put it immediately in the place it belongs, and they take the next card, put it immediately it belongs. That's effectively insertion sort. Now, how do I insert this value? By insertion, so here's the insertion. It means I want to end up with what? When I insert 1, 5, 8, 20. That insert means put the 8 in the right spot. And then the next value is going to be, I now have 1, 5, 8, 20. I'm reading what? 49. What I'm expecting to get? 1, 5, 80, 20. 49 happens to be the biggest, so it's going to be at the end. And then when I read the 9, 1, 5, 8, 20, 49. I read the value 9. What am I supposed to get? 1, 5, 8, 9. This is the value inserted, right? What is it? 20? So it's easy to write down the pseudocode for this, right? We start with an empty array, we read the current value, we insert it in the right spot, and then keeps going. It passes this array only once, right? For every value, it inserts it to the right spot. Of course, at the very end, when I finish reading, the array is going to be sorted. As an exercise, you guys can write that pseudocode. The question here is how this works.
Move elements greater than the current element to the next.
So I think it's obvious, it should be obvious for everyone here, that if I manage the insert part, how do I put the next value into the right spot?
Right.
I get it done. Who's with me on that? Good. That's for high school years for some people, college for others, right? If you have insertion sort in high school, you got this insertion part. But how does this work exactly if you have to implement insertion? What do you do? So how do we implement the insert procedure? Like take this 8 for example. What do we do? Concrete steps. We can put 8 at the end of this array just to have it somewhere, and then what? Compare to 20 and say, if it's smaller, swap it. And then compare to 5 and say, it's not smaller, leave it there, right? So let's take an example with this 9 here. How this insertion works. So what I have an array that's 1, 5, 8, 20, 49. That's my current array. And the next value that I'm trying to insert is 9. What are the steps? Compare 9 with 49. That, of course, the result is 9 is smaller, so that will result in what array? So actually, I should start with, initially I start with 1, 5, 8, 20, 49, and 9, right? That's my current value. I just put it at the end. So now I'm comparing 9 and 49, and I do a swap, right? So I end up with, let's write it right there. 1, 5, 8, 20, 9, 49. Now I'm here. I'm going to do what next? Compare 9 with the one on the left, right? 20. It's a swap or not?
It is.
Swap, so I do what? 1, 5, 8, 9,
20, 49.
20, and 49. Right? Next one is compare
9 and 8.
9 with
8.
8. Is that a swap?
No.
If it's not a swap, what do I do?
Leave it right.
I
Don't
stop.
do anything.
I don't do nothing. I say, I have it in order. The moment 9 reaches a value that's smaller than 8, it's guaranteed now that it's in order. The reason it's in order is because all the other values were in order to start with, and I didn't change their relative position. I only swapped 9, but the relative position of 1, 5, 8, 20, 49 remained the same. If they were in order here, they also in order here. The only thing I have to worry is the position of 9, which in here tells me I've got it in the right position. Good. Now, how do we write these down in terms of actual indices in an array? Who's 9? 9 is some value. It's currently the last value, right? Let's say, not n, but last. Who's this guy here? L minus 1, right? And now, who's this 9 here? It's still A of L. It's not the last. This is still A of L minus 1, right? And this is still A of L versus A of L minus 1. Of course, every time I swap, I have to do something with this L. And what?
Decrement by 1.
Decrease L, right? So when I say this, it's easy to say it like that visually, but you actually have to manage in an array who's 9, who's 49, so on and so forth. So when you write the pseudocode, you can't say swap 9 with 49. You have to say swap A of L with A of L minus 1. If that's the case, decrease L, move forward until you stop. Good. So far, I think this is the part that everyone knows about insertion sort, right? Just like in here, this was the part that everybody knew about bubble sort. I'm not sure how many people understood that they need an explanation for what's going on. Let's see if we know the remaining parts of insertion sort. How long does it take? One.
N minus 1 comparisons for every.
So it's a for I equal 1 to n, the outer loop that's reading input, right? And inside somewhere here, there is an insert. Insert into the current output that is sorted, right? Insert that value. So the value I'm reading is the input of I, right? I'm reading the next value, I'm inserting it, da da da. There's some other steps here. I think the n squared comes from the fact that this is an outer loop of n steps, and insertion is the worst case is not n, is how many things I have if I'm at step I. How big is that current output? It's I, right? In the worst case, I have to swap it all the way to the beginning. That means I, not n. The first time, I may have to swap one value. The second time, I may have to swap two values, so on and so forth. So if the worst case is theta of I get theta of 1 plus theta of 2, 3, da da da. If you sum it up, maybe you get n squared. I mean, that's for you to figure out, is it really n squared or not. This is not n times n. This is the worst case, 1 plus 2 plus 3. I think you can get n squared if you do that. But I'm assuming everybody knows that if this insertion really is a particular procedure. I'm going to write it in a more general way. More like a goal. Like, that's how insertion sort works, okay? That's true, but let's think about this insertion sort a little bit. How about we write insertion as, in a more general sense, find the right spot for that value, right? So I still have the current output, current sorted, and I have a new value, right, at the end. So insertion means find the right value, make space, put it in. That's a particular way to implement this. How does it find the right spot? It just keeps doing it. Right? It keeps swapping towards the left side. How does it make space? The swaps create the space. Every time I swap, the value that's being swapped leaves a space to put the one that's swapped in. Right? Every time I swap the 9 with 49, how do I get the space here to put the 9? 49 moves, so 9 can fit in. That's how it makes space. And put it in this procedure, we don't have to worry about it because when it's there. I don't have to worry. But somebody can say, wait a minute, I can do this differently. But it's not necessary to implement this way. It's quite possible to achieve the same result in a different way. I'm not saying it's possible. I'm saying if somebody does this, do we all agree that's a valid insertion sort? Yes. Even though it's not implemented in this particular swapping mechanism? So here's an idea I have. Finding the right spot can be done faster than linear. Why? Why can I do binary search?
Because it is already sorted.
Because that's already sorted. That's something, a big recap point. This is one of the items that's a failure in this class. If you don't understand binary search by the end of the term, which you're supposed to know already, you cannot pass, no matter what you do in the homeworks and exams, okay? So I have a sorted array, which is sorted due to the nature of insertion sort, right? We said that. It stays, it keeps the partially sorted thing. So I'm guaranteed that what I have so far, 1, 5, 8, 20, 49, it's already sorted. Binary search will find me the right spot in logarithm time. So I could do this in log n time. That looks like a big improvement, right? Because in here it takes n, worst case, or I, in there it'd be log of I. I could make space. So now, suppose I found the spot. This is my array up to I, and I have some values here, A1, A2, up to AI, that's sorted, right? That's sorted. And I found the spot. This is the spot. It's between this guy, this is the spot I need. It's between two things, right? This is the smaller and this is the bigger, and I need to insert that new value in the middle. How do I make space for that?
Shift.
So what I have, a sorted array. I found the spot much better than this method because I found it in logarithm time. But can I make space for it?
Maybe shift everything to
Shift everything. You know, I need to take this part of the array and move it. Move by one spot, right? That's what I need. Once I found a spot, I have to take the right side, push it by one to make space for the new value. Correct? Well, assuming on average, so on average, how many values are here on this side? Average. About I by 2, right? To shift I by 2 values to the right, how long is that going to take? That's all of I by 2. To move by 1 implies all of I by 2 shifts, right? You have to copy those values. By the way, be careful, you can't start from here to move to the right. When you move to the right, you have to move which value first?
Last
The
one.
right one. When you move to the left, you have to move which value first?
First.
The left one. If you move this value first, you just overwrite the
Overwrite.
next value,
Yes.
and then there's nothing else, it's destroyed the whole thing. We all know that? Primary school. When we move to the right, we move the right value first. You move to the left, you move the left value first. So not override the ones that you're gonna move later. Good. But this is gonna kill me, right? Because O of I by 2, even though I found the spot fast, just to move half of the array, I'm back to O of I, because the 2 here doesn't matter, right? It's like one. Why is that? Maybe because I have an array, right? Can I use a list? What if this sorted thing is not, sorry. What if this sorted thing is not an array? It's A1, pointer to A2, pointer to A3, pointer to, say this is AT and AT plus 1. That's the spot, right? I have an AT that points to AT plus 1, and then pointer to AI. That's the last one. So now I found a spot in here. How fast is it going to take me to insert the value in a list? Insert, easy, right?
Yes.
That's nice.
But
But finding the spot doesn't work. Why? Finding the spot
Binary
requires
search doesn't work.
a sorted what? Array. Can you find a spot in linear, in logarithmic time in a sorted list? Why not? How does binary search works? Why is it log n instead of linear? It jumps in the middle, and then it compares the middle value, decides out of a sudden, just with one comparison, reduces the problem in half, because it decides left or right. Now, if obviously with the recurrence, that is E of n is going to be what? Take one step plus n by 2, right? That's binary search. Master theorem, who's A, B, C? A is 1, B is 2, C is 0. It's n to the C. So n to the 0 plus 1 times n by 2, right? What's log base B of?
0.
So it's case 2, right? Log base B of A equal to that. So it's going to be
So n power c log n.
n at C log n, but C is 0,
So log
so
n.
it's log n. See? Master theorem is useful. Binary search reduces the step in half with everything. So why can't I use, what's the step, that magic, remember magic property? What's the magic property in binary search that allows me to do it for arrays, but not for lists? There is one key step in binary search. List and array look almost the same in sorted form. What's in binary search that in array works, but in list does not? There's one step in binary search. What's the exact step?
you basically breaking it into halves.
Hands up, because you guys, yes.
Breaking it into halves, you cannot do that with linked list.
Of course I can. I can break the list here, I got two
Yeah, but
lists.
you'll have to traverse till there anyway, because you're starting in the head.
Somebody else. There's an exact step in binary search that cannot be done with lists. What is the first step in binary search?
Finding the
Find the middle. Finding the middle can be done easily in an array because it's from 1 to I. Where's the middle? I by 2. Well, in a list, I know where the position is, I by 2, but I can't find that piece of memory location because to access it, I need to go from the front of the list, traverse I by 2 steps. Can't be done, find the middle, boom, in one step. So, now we've complicated ourselves, right? In here, I could find the spot good in logarithmic time, right? But making the space, it's a problem. In this other one, I could make the space right away, but finding the spot, it takes linear time. Right? I could implement it, find a spot of swaps like in before, with this would be no problem. So is there a way to deal with this? To say, okay, find the spot in logarithmic time, like with the arrays, and do also the insertion fast, not in linear, make the space, so to speak. Is there a way to do both of them efficiently, so I not do n square? Can I use this? If I use not an array or a list, not array, not list, how long it will take to find the value in a binary search tree? That's wishful thinking, log of n, but maybe. I can draw right now a binary search tree that will not take log of n. What a very degenerate binary search tree that looks like a list on one side. But some trees will be binary, will be log n. Obviously, how long it will take to find a value in a tree is the longest path, right? Because what happens in a tree, I do like binary search, right? So I compare with the root, tells me go there or there. The tree property will ensure that if I go to the right, I don't need to search the left side, right? If the value I'm looking for is more than 50, I'm certainly going to go to the right. So it's like in binary search, the problem with binary trees versus binary search in an array, y is not guaranteed to be logarithmic. In an array, I always chop in half. Am I guaranteed to chop in half? Yes. In a tree, when I say go right or left, am I guaranteed to chop in half? No. It's no guarantee that the left side is about half of the tree, or the right side. So even though acts like binary search, go either left or right, binary search is guaranteed to reduce the problem in half. If in here I go to the right, maybe the right is much bigger than half. So that's a little wishful thinking. Searching in a binary tree is log n time. Let's see. Let's hope. But how about the insertion? Suppose I found the spot here. What did it take to insert either this way or that way in a tree? Once I found the spot, how long it will take to create a child, add the value, da da da? O of 1. That's like in a list. So if I use a tree for insertion sort, I should be able to find the spot quickly and the insertion to be done like in a list in O of 1 time. The quickly part is difficult. It is true that in general binary search tree, there's no guarantee of log n time because we need the tree to be balanced. If the tree is balanced, meaning roughly all branches are about log n, then yes, finding a value will take log n. But there's no promise that the binary search tree is necessarily balanced. So what we're going to study at some point around spring break, it's red-black trees that take a binary search tree and add a little thing to it to make sure it's balanced all the time. So it will be like the general operations in a tree, additions, insertions, successor, predecessor, all those things, plus the balancing operations, who are going to ensure that this is always balanced. A balanced tree has the property that the depth from here to here is about log n, always. An unbalanced tree has a path, one path from root to the leaves, that's about n. Like a tree like this, here's a tree. What's happened here? This path, it's half of the elements, right? So this tree is definitely not balanced because it has a path about the size n. If I do binary search here, the worst case it's going to be on this branch, which means it's going to take linear time. But again, what we're going to study is how to balance binary search trees, red-black trees. That's going to ensure that after every operations, our trees do not look like this. Our tree is going to have depth n, which is going to allow me to guarantee that if I search in that tree, I can search the spot I need or the value I need in log n time. How many people knew that about insertion sort? That if I run to binary search tree, I can get to one in n log n. Okay, so we have three flavors of insertion sort. Insertion sort, as traditionally you knew about, it's with an array, and the swaps takes linear time, and then it's n squared. You can implement it with a list. Insertion will take nothing, but finding the spot in the list will take n. Or if you implement it with the balanced binary search tree, then it's n log n. Why? I still do the outer loop, which is n steps. But each insertion of the elements, finding the spot is log n in a tree, and insertion is nothing. It's all okay. I have also selection sort, but you guys can, that's easy. You can read it from the slides. The one that I want to do, I don't think, maybe we can finish. But it's one that most people haven't studied in college. I'm sure selection sort you guys have seen already. That's part of the recap. So make sure you can recap selection sort. Put it here somewhere. Recap. No magic about selection sort. I'm skipping it because for the other two, bubble and insertion, I had something interesting to say. Selection sort is just what you learned, nothing extra. How about heap sort? So first of all, what's a heap? We also have merge sort. By merge sort, we talk about recurrences. I think people understand how that works. Heap sort is somewhere here. So heap sort, first of all, what's a heap? Well, it's a binary tree. With values, of course. It doesn't have this property. That's too strong for a heap. It has a different property. We call this max-heap. I'm gonna, every time I write this max-heap, I'm gonna call it MP. Max-heap property. It's a much simpler property than the binary search property. This is a very strong property. This one, it's easy. It only says parent is bigger or equal to the child. Much simpler property. So what I'm going to do here, I'm going to show you an array, and on the other hand, how does this array looks like a heap. So here's the array, 16, 14, 10, 8, 7, 3, 2, 4, and 1. It's an example. So 16, 14, and here is the equivalent heap for it. 16 is the root. Then I have 14 and 10, 8, 7, 9, 3, 2, 4, and 1. Does this satisfy my property, my NP property? Max heap is every node higher than the children. This is a much, much loose property than something like that. Right? It doesn't have much to do with sorting. By the way, in here, if you have a binary search tree, how can you read it sorted? Somebody asked me, here's a binary search tree. Can you read the value sorted?
In order to
In order to traversal, get you done. This is not that easy. There's no sorting promise. So, here's how Heapsort works. So there's one more thing that I want to add here. this binary tree, in general, this is the definition of a heap for sorting. But I want to do something that makes it easier for us for this course. So we're going to use a binary tree, so that I'm talking about Heapsort now, the procedure. The binary tree is complete, completely balanced. So that's property number one, meaning what this completely balanced means. This tree has to have all the levels filled up except the last level. So it's not just balanced like in average balance. It has to have the only incomplete level has to be the last level. So you can have missing elements on this level. How many elements are on the first level? 1. Second level?
2,
Third level?
4,
Next 8, 16. The only level that's not filled is the last one. Okay? So all levels filled except last. So that gives me the counts 1, 2, 4, 2 to the k minus 1, and then the last is whatever I have left. Obviously, the last has to do with how many elements I have in the array. So that's not typically what's necessary for every heap, but for this chapter and for these assignments, you can assume all these binary trees are exactly filled up, so they're definitely balanced. Right? The going from here to here will take about logarithm time if all the levels are filled. It's very easy to prove that the maximum, even if all these level fills, is logarithm, right? So the depth of this tree is logarithm. That's equivalent. It's not equivalent, it implies the depth is about log n. Maybe log n plus 1, but certainly a balance. Now, obviously has the MP property. And it's maintained. Meaning everything I do when I break the property, I have to fix it. Maintenance means, so suppose you want to keep a tree balanced. You make an operation of it. If it's not balanced, you have to balance it. Now, how do I get things sorted out of it? Here's how the sorting works in here. I swap the root with a leaf, any leaf. For example, 16 with 4, right? I'll actually, for simplicity, let's say last leaf. That will make it easier. So I swap 16 with 1. And then I extract the last leaf, which now is the max value, right? Maybe I should write this in a, so now, so after the swap 16 with 1, what was the maximum value in the heap? 40. Maximum value has to be at the top. That's dictated by the MP property. If the child is bigger than the children, the maximum is guaranteed to be at the top. When I swap the 16 with the last leaf, the maximum is now in the last leaf. I extract last leaf. That's like in selection sort. Select. Effectively, I'm extracting the max right now because after the swap, the maximum is going to be here. And of course, I don't have the MP property anymore now. It's the one, it's going to be at the top, so I have to fix the MP property. But I think I have to fix it only for the root. Everybody else still has the MP property from before. If I started, 14 is still going to be bigger than the children. The only one that may not be bigger than the children is the root that was here. Right? So fix the MP for the root node. Now, everybody agrees this is gonna give me, let's see how that would work for that array. So the maximum extracted is gonna be 16, right? And then how the heap gonna look like? So actually, let's do the steps here. Assuming I already have the tree, the swap is gonna be, when I swap it, it's gonna look like what? 1, 14, 8, 7, 2, 4. That's not 1. After the swap, I get 16 in here. And then on this side, I get 10, 9, and 3. Right? And then I extract the 16. So that's the extract. So I write it down in my output here, 16. So extract means I delete this node. But now I fix MP. I have to fix the MP for the root, right? Because everybody else is in the MP order. So assuming magic property, I know how to do that. I should end up with what? 14 at the top.
10, 9, 9 and 10.
What?
9,
So 8 in here. All right.
you can take
In here is going to be the 10.
10.
So I think this stays the same. 9, 3. What happens here?
4, 7,
I think this stays 7. This becomes a 4.
2,
2 and 1.
1.
Maybe? I'm not sure. That would be valid. So then, if I'm to repeat this, what's the next step?
1 and
I do
14.
again swap, so that's the first element. Second element, swap. How things gonna look in a swap? I swap 14 with this 1, right? So then I get again 1 at the top, 8, 7, 10, 9, 3, and in here I get 7, 4, 7. This is a 2, and this is the 14.
The one has 7 comes attached to it.
7 here, and then this is a 4.
And 2.
Again, extract, this delete, 14. And then I fix from here, fix MP, it's gonna result in what? 10 at the top. This will remain the same, 8,
4, 7,
7,
2,
2. And this branch is gonna be 9,
3.
1, 3. How many people with me on this? Good. So I think I convinced you guys that it works, right? Now there is a problem to build it first. So here, this is a build part. How do you get to even start? How do you get to here? Right? So that's one problem. How do we get to here? The other problem is, I think you guys see the swap very easily. Swapping is no problem. Swapping the root with the leaf, that would be no problem. Extracting the leaf, it's easy, right? I just delete the edge and write that thing down. But then fixing the MP property, that's not so easy maybe, right? So actually, there is a procedure that's the fix MP that does the whole lifting, both in the building. The key procedure here is this fix MP for some node. So the fix MP, of course, is the procedure I need here. it's gonna be the one that's gonna also help me build the thing in the first place. So the fixed MP of a node assumes the right and left subtrees have the MP property. So I'm going to describe a procedure that does the fixing starting at some node, any node, assuming under that node stuff is good. So I'm going to assume that it's fixed under it, not on top. So this 14 in here, to make sure I do deal with the 14, I'm going to assume that the left and right subtree under 14 are correct, but not the top on the right side. I'm not concerned with that, right? So this procedure is very easy. Floats down node down as necessary, or if necessary, by swapping with highest child. That's it. Floats means it keeps going down. So imagine here, I have to deal with this one, right? I'm going to compare with the children to see if I need to fix it, right? Remember what the property is? The node has to be higher. Now if both children are lower, I'm done. Now it's not the case. It's not lower. So which one do I swap with? The highest child. So I swap the one with 14, but then one is here. I keep floating it down. I ask the same question. How is one compared with the children?
Smaller.
There's a bigger child than it, so I'll swap it with
8.
So I move one here, 8 here. Now one is here. I ask the same thing. Swap it with
4.
the 4. And that's how I float this down. This is a very simple thing. Again, floats down means until reaches correct position. Correct means what? The node is now bigger than both children. How many people understand this? I take a value, I float it down by swapping with the highest child until both children are smaller than it. How long is that going to take? Assuming this is a full, complete binary tree, so it's log n time, right? It's not like in the balance tree. I'm guaranteed to be log n time in here. This is going to take log n. Theta of log n. Because the depth of this, even if I start at the very top and I go all the way to the bottom, is no more than log n swaps. And it's easy to see that's O of one operation to compare and swap. Right? So this is the property that fixes the MP, but it's absolutely critical, this part here. It only works because it assumes the subtrees are already fixed. You can see how this floating down works if this is already has the MP property, but it doesn't work if this is a mess. Are we seeing that?
Yeah.
It needs this to be, because this will remain in relative order even if I float one through it. So, but if I need to fix this subtree too, that will be a problem. So what's the only thing left here? I think everybody believes me that once I build it, I can do this. If I start repeating this, so this is a build, this is a loop here. Right? Loop, loop, loop until I get everything out. How many times I need to loop this part to do the extraction? What's the next element? 10? That's going to loop n times, right? And how much is going to take? Swap takes what? Nothing. 1. Extract? 1. How about the fix? So the whole thing is going to be? And log. The only part that I didn't talk about is the build. That's something we're going to have to figure out next time, or you can tell me how it works at office hours. How can I build this thing? I can give you a hint, but we'll do it Friday in class. First, I read the array and I just dump it as it is. in a complete form. So I literally write 16, 14, 10, da 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 da. But then of course that's just gonna be a binary tree. It's not gonna have the NP property at all. So I have to start fixing it. But how can I fix it in a way that I can make this assumption? Remember, NP requires the subtree to be fixed. So suppose I've built my tree. Remember, it's complete except for the last level, right? So here's one that's complete, except for the last level. Maybe the last level only has 3 elements. I literally put the first element here, the next 2 in here, the next 4 in here, the next 4 in here. This is a binary complete tree, but it doesn't have the max-heap property at all. I want to run this property to fix it. But I can't run it at the top because the subtree is not fixed, right? This property assumes the subtree must have the NP property. But where can I run it? I can run it from the bottom because in here I don't need to run it, but in here, can I run it in here? Can I run here, say, assume the subtree is fixed? Yeah, because subtrees are just one element. So if I run this fixed NP from the bottom up, maybe I can fix this whole thing to get done. There's a build part I need to do first before I start extracting. So we'll recap that next time. Right. So the plan with office hours is I'm going to be at office hours in principle Monday and Wednesdays. The TAs to answer grading questions will be at office hours Wednesday and Fridays. Office hours are at 6 p.m. in room 166. Do you mind stopping the camera? It's a red button on, yeah.